I would first like to say that all of this that we're gonna talk about is a collaboration with my student Zdeněk Kastner, who basically, I mean, he did most of the experiments, right? Definitely, I'd like to give credit where credit is due. So that's a lot of the work has been done by him. We collaborate for several years already on this topic, and I hope it's gonna show a little bit on basically what are the neural language models, kind of how they are trained, and how can they be used, where they fail, and some of our experiments where we try to basically fix the problems that the large language models are having in language generation. So I'd like to first introduce a little bit the problem of natural language generation. I guess right now it's a bit of a wider area, so I'm gonna focus in this lecture on data to text generation, which I mean, this is what natural language generation as a topic used to mean, but now it's broader. So what I'm going to be talking about is data to text language generation, which means converting some kind of a structured data such as RDF triples, dialog acts, or database tables into text. So you can imagine it like this on this small example. So you have some RDF triples and some NLG model that converts them into a sentence. So basically, you have two attributes of a certain pub, and you have them described in a sentence. The usage of data to text NLG is mostly either in some kind of reports based on data. For example, you can generate sports reports from some kind of results tables. Or you could generate weather reports. Another very prominent usage area of these systems is dialogue systems or conversational assistants or smart speakers, if you prefer those terms. So if you have Alexa or Google Home or Siri on your phone or in your home, you definitely know this. So the responses of those systems are basically using natural language or data to text generation. So this is just an example that I took from my own computer, just on Windows. You have the Cortana assistant, and it's basically the same thing. So that's our problem. Let me just change right so I can draw. Okay, so now in language generation or in data to text generation, the most prominent method used to be, and actually continues to be, templates. So it just means that you have a sentence with some kind of blanks left over for various different variables, and you just take the values of the variables and fill them in, and you have the sentence. So this is still used in most commercial NLG systems. It's safe, it's tried and tested. The problem is that somebody has to actually write these kinds of sentences. So every kind of sentence that you need needs to be written. And that also means that the fluency of those sentences might not be so great. There have been some alternatives, such as using a rule-based pipeline or some kind of a grammar, or a pipeline of statistical models, but these did not bring much better results and are not so much in use nowadays. The research state of the art nowadays is neural models, and particularly large neural language models. And the difference in their operation is that in comparison to those rules and pipelines, they usually operate in just one step. So you just feed in the input and you get the output. They are also able to train fully from some input-output pairs, so you don't have to, write rules or handcraft the templates. You can just give them some examples and they learn everything. Also, the outputs tend to be much more fluent than what you could get with templates or with rules. So this is actually like the killer feature of these models, that they really produce outputs that are lifelike. The problem is that it actually needs more training data. So you had to handcraft something, but right now you need quite a few examples. So you need like thousands, maybe tens of thousands of examples to be able to generate in a certain topic or in a certain domain. And the main problem here is that those models are kind of opaque. It's a black box, basically. You just feed in something comes out, and you have no guarantee that what comes out is actually correct or is actually accurate and actually reflects the input. Let me show this in a bit more detail here. So what I mean by accuracy or by semantic correctness is basically getting the output to correspond to the input. And there are two basic types of errors that may happen during NLG. The first one is hallucination, and it's something that's been talked about quite a lot. And that basically means that you have an output that is not grounded in the input. So it looks like as if the neural model hallucinates something or makes something up. The other problem is omission. So part of the input is actually forgotten by the model. If you look at this example, you can see that you have the same two RDF triples as we had in the previous example. So you have an information that there is a pub, and that pub is in the Riverside area. And if the NLG system creates a sentence like this, you can see that actually, the information about the place being a pub is completely omitted from the sentence. So that's just missing, that's forgotten. On the other hand, there is a bit of information that the model basically made up or hallucinated. So this can happen in neural generation, and both of these errors happen relatively frequently, definitely more frequently than we would like. You can measure basically the error rate of these kinds of occurrences. So you kind of compute how many of those triples are verbalized correctly, and how many kind of triples or pieces of information have been added using basically, it's kind of like word error rate in speech recognition. It's just over pieces of semantic information. So this is what you measure, the slot error rate or semantic error rate. So that's the accuracy. And now let's look at like why this is, or why this can happen. So if you look at the most prominent or the state-of-the-art architecture that underlies all the neural language models of today, that's the transformer architecture. And I mean, I've drawn a very crude diagram of this architecture. Obviously, the whole neural network is much bigger. You have more layers here, and you have much longer spans of text. So here we have just like 2 tokens of input, and it generates basically just 2 words. But let me just talk you through the diagram a little bit. So you represent basically the first part of the network is called the encoders. That basically takes the input, your input data, the RDF triples or whatever you start with, that you linearize into some kind of a sequence. So here it's the most simple sequence that I could think of, and you encode it. You somehow process it by the network to create a representation of its own. And to do that, you basically have embeddings of each of your input tokens. So for each of the token of your input representation, you have some kind of a vector of numbers. So kind of imagine the numbers all around here. And you just feed these individual tokens represented by their numbers into the network. And you connect it with the so-called positional encoding. So in order to kind of indicate a position in the sentence for the network, because the rest of the network is kind of agnostic or doesn't know about positions, you also add in some kind of, basically it's another vector of numbers that indicates the position. And those vectors could be trained or they could be static and fixed for a given pre-specified for each given position. And then you have basically just a series of blocks or like a compound layers in the network, where the first layer is so-called attention, which is basically just a weighted combination of all the inputs that kind of come into the network. And then you have basically a fully connected or feed-forward part of the layer that is using ReLU activations, which the ReLU function basically looks like this. So basically, everything that is under 0 is zeroed out, and what is positive gets just propagated to the output. So that's how the encoder part look like. So you first basically just take all those input tokens from the input representation, and for each of them you get some higher level representations in the network. And in the decoder, you then decode the output from those representations just word by word. You use, again, some embeddings for the target words. So each word has an embedding. And that's, again, a vector of numbers. You have a specific word or token that is a starting symbol that you feed to the network at the beginning of the generation. And then basically the network works exactly the same. You have the same types of layers. And the only thing is that your attention layer looks at the whole input as well as the preceding output. So the attention has like a longer span, but otherwise the layer is exactly the same. At the end, you have a softmax layer that gives you a probability distribution over all the possible words that can be generated at this point. And you just pick one. You may pick the most probable one, and that word gets fed to the next step of the generation. And that's the input to the next step of the generation. And again, you generate the second word, and you continue like that, generate the third word, and so on and so on. So basically, word by word, you generate the whole network. So the whole network works this very much low levels. So the representation inside the network is completely opaque. You don't know what the embeddings mean. You just feed in the input and then try to generate the output word by word, one by one, based on what you previously generated and conditioned on the inputs through attention. So that's the operation of the transformer models. And now one more point regarding to how they're trained, because if for the training, you basically just train the model to take in some kind of input and a bit of output, some kind of preceding context of the output, and you just train it to generate one word at this position. And here, that the correct word should be expensive, right? So that means that if the network generates the word expensive, there is no loss. That's correct. And you're happy. If the network generates something else, and this is penalized, that incurs loss, and you train it to do something else, and it's completely fine, because you don't want to say that it's cheap. The problem is that even if the network generates something that is actually synonymous to what you want to generate, so the word pricey would have been perfectly fine in this position, right? You still penalize that word, so you still incur loss for this word. So you need to have the exact same word at the exact position. It's a cross entropy loss. So basically anything apart from the correct word gets penalized. And this is the same case if even if the correct word would be generated somewhere else in the sentence, it's still wrong for from the point of view of the training. So in here, you generated a different word, so it gets penalized. So it's really very low level in terms of the supervision. What comes kind of in addition to this is the so-called pre-trained language models or large language models. But the only difference compared to what I've just shown for the transformer models is that you have a lot of data and the model is slightly larger, so like more layers, and that's basically it. And you have a lot of data, and you cannot usually get enough data for like your data to text generation task, so you don't have like enough pairs of structured inputs and some sentences. So what you do is work with text to text, and you basically try auto encoding or denoising to pre-train the model. So you train the model to, for example, generate some kind of correct text based on a mangled text that has some parts deleted or that has some parts permuted or rotated. You know, there are multiple these kinds of low-level tasks. So you can kind of imagine that, you know, you have a sentence that looks like blue, expensive, spice, and you train it to generate this. And you can basically create many more sentences out of one correct sentence. So, and you can take any sentence from the internet. So there are basically those models are trained on gigabytes and gigabytes of text, where, you know, you can just download anything, any kind of English text or whatever your target language is, and pre-train your model on that. So you first pre-train the model on this data set, and it basically gets a very good view on language. And then you fine tune the model on your task, which basically means that you continue training on the actual data that you want to work with. And those pre-trained models are available online, so you can just download them and fine tune yourself. So that's the pre-trained models. I can just show an example of some experiments that we did with one of the pre-trained models. We used a so-called MBART model, which is pre-trained in multiple languages, and we've represented our data like this. So this was RDF triples. These were just represented as kind of text with a lot of pipe characters and these weird triangle characters. But we trained the model, basically we fine-tuned the model to generate English or Russian text, and it worked pretty well. It worked surprisingly well for Russian, to be honest. And this was actually part of a competition or a shared task competition, and we did pretty well just by fine-tuning and then pre-trained language model. So the outputs were really fluent, but there have been some problems, especially in cases where you know, it hasn't seen some kind of a predicate in the training data. So for example, this population metro predicate wasn't seen in the training data. So the only thing it was able to do with it is this. And I mean, it's, you know, this is not a nice, I mean, this sentence doesn't really make sense. So that's a problem. And another problem is that there are some kinds of hallucinations that basically connect unrelated triples. So if you have a person that resides in Istanbul and you have a birth date, it can potentially say that that person was actually born in Istanbul, and that is incorrect. So these kinds of errors are there, and they do happen, and they are definitely a problem. So we wanted to somehow get rid of this problem, and we tried basically to work around it or to kind of bypass this by bringing in a little bit of the old methods. So we actually combined templates with a neural model. So we used templates to represent the individual triples. So you know, for the individual parts of the input, for each of them we have a separate triple. So that's actually kind of additional piece of data that we need to get somewhere. So these individual triples have their textual representation. And the idea is that the neural models will work with just text, and the operations they will do would be basically similar to what they were pre-trained for. So instead of, you know, doing the like fine-tuning for this task and fine-tuning for this kind of weird language, the only language they will be working with is, I mean, English in this case, or natural language. And you actually don't need so many templates. In this case, we needed slightly above 300. And you know, these templates, if they are handcrafted, they are guaranteed to be accurate. So you're losing no information here. And you don't even need them to be like perfectly fluent, because this is the task of the neural model. So the neural model is just taking those templates or the templated output and is trying to make it more fluent. So we called this operation fuse and rephrase. So it fuses those templates into sentences and tries to rephrase it so that it becomes more natural. So it's basically actually a pipeline of 3 steps. In the first step, those things are ordered. So, this comes first, this comes second, third, this comes second. And in the second step, those things are actually aggregated. So we kind of insert sentence boundaries. And in the last step, we have this representation that says, here are the templates in this order with this sentence boundary, generate a sentence. So this is actually the sentence generation task per se. The only difference is that the input to this task is not this kind of structured representation, but is actually the set of simple sentences and the separators to indicate which sentences need to be joined, and the output is shorter compressed sentences that join the same information. And the idea is that we're doing just what neural models are good at, which is ensuring fluency of the outputs. And they are just shifting words around, so they don't have to have like a complex kind of correspondence between the input structure representation and the output words. So there is basically less space for some semantic errors. And there's actually another really nice property, and that is apart from the templates, we actually don't need any additional training data. We can just use general domain data that we collected from Wikipedia for this task. So we can basically work 0 shots. So that's like a really nice feature of this approach. I'm just going to show how we get the data. I mean, the idea is that we have basically 3 neural models, and each of them just does one step. And to get this data, we just take sentences from Wikipedia like this, and these are the targets for us. So this is what will be the output, and we generate or we create synthetic inputs that are then that we use to train our models to produce this. So the actual operation will be this way, or this is what our generator will do. But to produce the data, we actually go backwards. So we actually split the sentences so that we have just one piece of information each. There are some neural models that are able to do this. So we do that. We actually replace pronouns with the full expression. So the sentences can be can stand alone with and then we can also kind of swap the order. So that's what we do for to get the training data for our pipeline. So then we can train models to do ordering, aggregation, and paragraph compression. And we just took like 1 million sentences from Wikipedia. We could even take more, but this was just about enough for our computation needs. And this is like much more than you can ever get for a specific domain. And what we get is actually pretty good accuracy, which is perfect in like a simple domain. So in a simple restaurant domain, we basically get almost no hallucinations, almost no omissions. It's a little bit worse for a more complex domain where you have DBpedia information, but it's still better than all the neural models. And the fluency, if you look at Blue Score as some kind of indication of fluency, is slightly worse than previous models. But if you look at the outputs of our model, you can see that these are perfectly fluent sentences. They are perfectly fine. They might not be as colorful as the ones generated by previous models, but otherwise they are perfectly fine. The problem, especially for the WebNLG DB data, is there is still a little bit of hallucination. So here you actually see that if there is an information of Rome being capital of Italy and this car being assembled in Italy, the model somehow connected those two and said that it's assembled in Rome, which is actually not true. So this is still a problem, but the model can be further improved by various even basic methods such as filtering the outputs or trying to, evaluate the outputs and choose one of multiple generated outputs. So generating more and then ranking to get the best output. And so that's our take on like how to bypass some of the problems of neural models in generation. And I'd like to show just, I know that I'm going over time, but I'd like to show a little bit of or an approach on how to evaluate or how to take a generated output and see using neural networks if this is okay, because evaluating a natural language generation is a problem on its own, especially automatically evaluating, because otherwise, yeah, obviously you can always give those sentences to people to read, but that's expensive and you cannot do it on a daily basis during model development. So you have n-gram-based metrics derived from machine translation, but these aren't very accurate, aren't very reliable. You have some neural metrics that kind of work, but it's a question whether, how much is accuracy, how much is actually just about fluency. Then you have the semantic error rate or slot error rate, as I mentioned, but that usually on most data sets is using just regular expressions. So somebody actually has to write a script to evaluate for a given domain, and that script is just regular expressions. So that's kind of beside the point, or defies the point of using NLG in the first place. And proper evaluation actually means full natural language understanding. And the thing is that pre-trained language models are actually pretty good at natural language understanding like tasks. There have been many, I mean, there are people that know much better than me, but there have been many benchmarks and tasks where they even surpassed human performance or got close to human performance. So the idea is, why not use them? And the task that we chose for this is natural language inference, which is trying to basically relate two sentences together. You have a premise and you have some kind of a hypothesis. And in some cases, all the facts in the hypothesis are included in the premise, and that means entailment. Or they could be kind of neutral. So, not all the facts are included, but it's not contradictory. But in some cases, it's a contradiction. So basically, this is natural language inference, and this is what it can do. And there are models that do it pretty well. So the idea is we just use a model trained for NLI for inference and check whether the input data entails everything that was generated and whether everything that was generated entails the input. So that's the idea. So if the data entails the text, there is there is no hallucination. If the data or if the text entails the data, there is no omission. And we again just use templates to represent the data, same as in the previous experiment. And I'm just gonna kind of jump through this so that we so that I don't spend too much time for it. But the idea is that you first check whether, for each single fact that is represented by a template, you check whether, the fact is entailed by the generated output. So the premise is your generated output, and your hypothesis for NLI is one fact from the input represented as a template. And you can see that in this case, this is an omission because that fact isn't entailed. In the second case, this is actually entailment. So this fact is inside that. And these numbers are actually scores from the model. So this is what you can do to check whether all the facts have been generated. And the second step is to check whether the model didn't make up anything, didn't hallucinate anything. And here you can see that you take the concatenation of all those templates representing the individual facts as your premise, and your hypothesis is the text. You cannot easily split this into multiple checks, so you just do one check. And here you can see that the entailment is not there, the relation is neutral, so this is a hallucination. And so this is basically how you can check this. You can actually output multiple things, multiple classes for this. But the main idea is this, that you check using language inference for hallucinations in one direction, for the omissions in the other direction. And if you actually evaluate this, and we used, again, the DBpedia data and the restaurant data, and we compared to human ratings gathered through crowdsourcing, so from people on the internet, and against regular expression semantic error rate scripts. And what we got was, if you compare, then the agreement is definitely not perfect, but if you check manually, you can see that basically like half of the errors of this method, of our method, are in fact correct and are wrong in like according to the human rating, so or according to the regular expression. So there is some noise in the annotation and some noise or some problems in the regular expressions coded for the domain, and basically we are about at the same level of accuracy as those other methods. So this actually works pretty well. So that's basically what I wanted to say. To sum up, you have really fluent outputs with neural methods, and that's especially true for neural pre-trained models based on the transformer architecture, but they are not guaranteed to be accurate. There's lots of omissions and hallucinations, but there are some ways to make those outputs more accurate. What we did was combining the approach with using templates and basically using or constraining the neural component to only just editing the text to make it more fluent. You can actually use pre-trained language models for language inference to check for errors in generated outputs. And this works relatively well. It's not perfect, but it's pretty good actually. And there are obviously many other approaches that can increase the accuracy. You can clean your data, you can do some re-ranking, you can train for additional tasks, you can constrain the decoding. And there's actually more to come, which will be part of my ERC project, where we want to work more with inference, but on like a symbolic representation based on various semantic formalisms. But that's kind of future work for now. So that's all I wanted to say. Thanks for listening. Again, yeah, this like most of the experiments have been done by Zdeněk. So here are some contact links for me, both me and him. And I'm happy to take any questions or engage in the discussion.
Thank you very much for the presentation, Ondřej. Thank you. So I will stop the recording now for the discussion.